I hope you enjoyed the new opening video. And if you pay attention to what we have played before the class, the name of the song is called Clock from Coldplay. So today, you know, we are going to talk about something related to clock. But before we start, let's bring something back to your mind because that's really important that you keep some sort of memory before we have the midterm so that you know like where we are and where we are coming from. So in the last lecture, we spent a lot of the time talking about the floating point ALU design, and it turns out that there are some anomaly in the floating point execution, and it's not because the programmer, it's not because of the hardware itself as the bug. It's just because there are limitations on the hardware design. So you should treat this as hardware features that you as a software programmer, you should know. So that's why we have this class in the curriculum, because we want you guys to be aware that there are some hardware limitations that your software, even though you have the very, very good software, if you are not aware of this, if you are a very good software programmer, if you are excellent in algorithm, but if you are never paid attention to this kind of hardware features, you will still be a programmer who produce bugs all the way, and that would waste a lot of your time in your life. So that's why we have to learn things like that. So in addition, right, as a software programmer, you should know that for representing numbers, there are many different data types you can pick. And what's the strengths of each data type? What's the weakness of each data type? So for example, there are 3 different formats that are right now standardized in the floating point format that are they are like 16-bit half, 32-bit float, and 64-bit double. So as you can imagine, the more bits that you need to express a number, the bigger the hardware it needs. And as you learned before, it will require longer latency to calculate the arithmetics between 2 numbers. On the other hand, if you have shorter bits, then it turns out that the calculation throughput, the speed, the area, the power consumption will be all lower. However, what you are sacrificing is the precision. So the number that you can express, the precision, the accuracy, the number that you can present with fewer bits are actually worse. So you have to be really careful about where you use them. So if you have applications like neural networks, artificial intelligence, trust me, you can use less precise data types because you know, like if you trust the theory behind this architecture, artificial intelligence is mimic the human's brain, and you know, like being a human being, you know that how vague our memories are, right? So so given this, right, there's also no point for your computer to be really precise on artificial intelligence. So that's one thing a lot of people have the misunderstanding about, like, oh, today we can do artificial intelligence is because our computer reach circumstance that we can calculate numbers really precise. We have larger data types. That's completely wrong. Nothing related to nothing in DL relies on high precision data types. And again, right, what data types to use is a trade-off between area efficiency, cost, performance, and accuracy you want. So if you are designing an application like we played in the opening video, like launching something on the Mars, you really want very, very accurate data types. So after this, right, we know that, well, we have talked before. They are so-called combinational logic, like the LU in floating point, the adder, anything that we talked so far, they are combinational logic. And this combinational logic, they are pure functions of its current input, and output doesn't change no matter how many times you invoke the logic. However, there's another type of sequential logic. It has memory, so its output will depend on current inputs, previous inputs, and their history. So and because the difference in their natures, the theory behind it is also different. So computational logic is based on Boolean algebra, and for sequential logic is based on finite state machine. So talking about finite state machine, through the last lecture, I'm wondering for this question. So if you are willing to take the survey that I pulled now, can you guys let me know how many of you heard about finite state machine before the class? Okay, so looks like there is a good number of you learned finite state machine before the lecture. Then it becomes really odd to me that when we talk about finite state machine, when we have questions on that, then why the poll result is kind of not reflecting that, right? So we are so to make sure that you guys really remember what finite state machine is, today we are going to have some more practice so that I will feel more confident that we can proceed. Because as I mentioned, finite state machine is the whole theory behind the sequential logic, right? So this is an example finite state machine. So you have an initial value, you have an initial value or state, and then you have transitions, which we represent as signals here. You may output something during the transition, and you may reach a final state, right? So that's the finite state machine, right? So so finite state machine is basically a collection of those things, and you can represent them in a state diagram like I draw, or a state table like this one, right? So the last time we talked about this question is actually a sequence, or say a token recognizer trying to recognize the token 001 from Mars. And the most popular answer at that time was C, which saying that you guys think only two states are enough. However, it's not the case. So right now, I'll continue on this discussion. So let's give you some complete recap on finite state machines, because these are really important. And if you cannot draw a finite state machine, it's really hard for you to get things right. And then we are going to talk about the very, very basic form of memory. As we mentioned that memory is one of the important features that sequential logic would give you. And finally, we are going to talk about clock, which is related to the song that we play. All right, so let's talk more about the finite state machine. So since you guys mentioned that you know finite state machine before the class, would you guys mind to show me your understanding about finite state machine through this question? Question?
I was wondering, I don't really get the question.
The question is this: what's the longest string this finite state machine can recognize without visiting any state more than once?
Yeah, I kind of don't.
If you go through the finite state machine every state exactly once, what's the longest sequence you can recognize?
Okay.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. From your poll result, I'm sure right now a majority of the class doesn't really get the idea of finite state machines. So please pay attention to finite state machines. Okay, so for this question, right, anyone has thoughts? Okay, so I have Xie Xiangying.
Oh, I put down C because so basically you can go from S0, S1, S2, S3, and there are 3 transitions.
Right. Yeah. Right. So here's the thing, right? If you want to recognize the longest string, you need to find something that would allow you to set, well, my initial state is S0, and and the transition would help you to go through from S0 to S1 to S2 to S3, right? So if you want to do this, how long the string is? Right. So the thing is that, right, first of all, you start from here, right? That's the current state. You need to transit to one state after you read another string, right? So 1, 2, 3, right? So if you want to visit any state without more than once, only 3, right? Yeah. So not 4. Okay. All right. So given this, right, that kind of like tell you why for the Mars you need more than 2 states, right? So right now, let's look at this one, right? Let's try this again. What's the longest string this finite state machine can recognize? Okay, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, I saw some of you have a question. Do you mind to raise your hand again? Okay, so for this question, right now, I can see, well, this time you guys get it, right? Most of the, about 76% of you got it. It's 2, right? So the answer is B, right? And the reason, again, right, if you thinking about how can I go through as many states as possible without revisiting any of this, right? You still have to start from S0, and then you still have to start from S0, and then you go to S1 and go to S2, right? And this will take 2 transitions. And if you start from anywhere else, that won't give you, like if I say I start from S1, right? S1 only allow you to go through these two states, right? And if you start from S2, you can only go from S2 to S1, right? So you won't be able to go to S0. So you have to start with S0 anyway in this example, right? So what this example tells you is that, okay, if I create a state machine like this, then I would need if I want to create a state machine that recognizes two characters, right? Then 3 is probably the number to start with, right? So let's generalize it. So if you have a string S and a finite state machine N that accepts and recognizes S, then if your if your string length S is greater than Q, which is the total number of states, then when the finite state machine processes S, it must visit one more states more than once, right? So that's not and sometimes it doesn't work out in that way, right? So you can't in the very beginning, you cannot assume that your states are fewer than your string length. And sometimes you would also need to consider the case that, well, there are some substrings in the S or some substrings before or after, right? So you must be able to accommodate those cases when you design your state machines, right? So this is the generalization, and because this is just a logic design class, right? If you don't remember what's happening, and if you don't know what's happening right here, right? This is the class you should start to figure out, oh, what's wrong with my understanding about finite state machine? That's CS150, right? The Introduction to Theory of Computation. I think the whole book is talking about how to draw a good finite state machine, finite automata, this kind of stuff, right? So if you cannot remember what's going on there, read a book, right? And that will help you, right? Okay, so right now, given we are on the same page regarding how many states can recognize how long the pattern is, right? Do you mind to go back and look at the finite state machine for life on Mars and pick the one that you think that would work out? And let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now, let me see. Okay, I think we are better, but currently I don't want to announce what's the right answer or what's the most popular answer, but I need someone to tell me, how do you think? How do you solve this question? Because I think it's more important about problem solving. Can some of you share with me? Okay, 谢谢祥英. Okay, you're the hero of the day. What do you think?
So I pick A because you want to have so you see so C 001 output 1, so you want to only output the 1 after you see a last input of 1, and that only happens for A.
Right. So if you go through this state machine, right? So well, if I give you a question like this, right, then that becomes easier that you can, in a worst case, you can just go through every state machine and see what's going on there, right? So if I start with S0, and if right now I see a 1, right? If I see a pattern starting with 1, that's definitely not something I want, right? But
Yeah.
if I see a pattern start with 0, then there is a potential, well, this is something I need, right? And then I go to the next state, right? And then right now I have 1, 0, right? So what I'm looking for is that I can aggregate 2 zeros, and after that should have a 1, right? So in S1, you should have at least 1, 0, right? But you should have exactly a 0, right? But right now, if you meet a 1, then it means that, okay, everything right now has to start from scratch, because 0, 1 is not something we are looking for, right? But if you get another 0, right, then goes here, right? So and then if you see another 1 again, right, then we should output 1, because that's what we exactly want, right? And some of you, well, I think the second most popular answer is C, because some of you probably not aware of this difference, right? Um, so, well, yeah, I don't see how this one would be right? Because for this one, okay, for this one, right? Okay, I guess what you are thinking is that, okay, let's start here, right? And you have 0, 0. So you have 0, right? And you got 1. So this part seems right. But what's wrong is here, right? Because what it tells you is that if you have 0, 0, 0, 1, 1, and forever ones, you are still going to be in a state that recognize that. That would output 1. All right. Okay. So thanks.
Yeah.
All right. So Senyue, do you have question? You're unmuted.
Uh, I- for the B, for the
Uh-huh.
B is like 001. You say
0, 0. So you say 0. Well, for B, how? Well, for 0, 0, 1, right? But
Yeah.
for B, okay, let's look at B. For B, for B, so you say I start with S2, right? And then I have 0 here. And then if I keep getting 0, I will stop here. And if I get a 1, I would go here. So okay, so this one is essentially treating S1 as S2. Is that what you want to say?
No. I just say it's like the output is same. It's 001.
Yeah, but what if other patterns come in?
Okay.
Right. So that's the thing, right? So for this question, I would say only A is the answer we want, right? And okay, so right now it's more about okay, Xiangying, question.
Oh, I'm just saying, like, for B, if you look at it, like, starting from S0, we can get 0, 1, then 0. So that can potentially lead to incorrect pattern. So
Right. So that's what I would like to say, right? Okay, Fang Zong, question.
Can you explain why B isn't correct again? Because I didn't.
Well, so Xiaoying just said, right? If you are currently at S0, right, then it would give you the incorrect result, right?
If I input 001 from S0.
0, 0. Okay, so Xiaoying, do you want to go through again? What was the case you mentioned?
oh, I mean, like, you go from S0 to S1 and S1 to S2. So do you get 0, then 1.
Oh yeah, if you have a
That's-
0, 1,
that's
right?
not right.
Then it's incorrect. Get it?
Professor,
Yeah.
I'm actually kind of confused too. So when we say if C's 0, 0, 1, then we just want the outputs to do 0, 0, 1?
Yeah. Only if
Okay.
you see 0, 0, 1, output 1. If you see 0, 1, 1, it shouldn't.
Oh, I get it. So you're basically saying that
And
the
your
output should
state
be 0, 0,
machine
1.
could be current. Yeah, and your state machine could be currently in any state of the state machine. And it has to be correct anyway.
So you're saying that B is wrong because we could have other possibilities of getting something different than 0,
Right.
0, 1, but A ensures
Yeah,
that you
so
get 0, 0, 1.
right, only 0, 0, 1, right? But for
Okay.
B, you can also get 0, 1, right?
Yeah, okay, I see.
Yep.
That
And
makes sense.
for this thing, right, you can also get 0, 1, 1, right?
Yeah, that makes sense. Okay. So
Okay.
basically when we say if C 0, 0, 1, we just want it to output, we want the outputs to be 0, 0, 1 and the final output to be 1.
Right, you don't want any exception.
Okay, I got you. Thank you.
Okay. Fan Zhong, question?
Yeah, you said that B fails some cases. What
Yeah,
is
0, 1.
0, 1?
0, 1 is not what we want, right?
I still don't understand. It's not making any sense. So you
Okay,
start
so
from
right now, my state is as S0, right?
Right.
If I get a 0, right, I
Mhm.
go to S1. If I get 1, output 1. 0, 1. It's output 1. And that's not what we want because we only want to see 0, 0, 1, output 1.
Okay.
Right? Get it?
Yeah, okay. I see. Thank you.
Okay. So right now, I think most of you are doing this traversal stuff, right? But remember, what was the reason why I want to tell you in the very beginning how many states we need to recognize a certain length of the sequence? It's because this actually tells you a systematic approach to solve this kind of question. So we said we want to recognize 3 characters as a pattern. Then through the previous questions that I asked you guys, we need 4 states, right? So that was the default. We need 4 states, right? So if we need 4 states, then what happening here is that, okay, we start with S0. If we see 0, if we see a 0, we go to the second stage. And if we see a 1, we have to go back. And if we see another 0, we go to the next stage. So S2 is actually meaning the state that I am aggregating, I'm accumulating 2 zeros in hand. And again, if I see another 0, I have at least 2 zeros in hand. And if I see another one, right, then it should output 1. And that's actually the final state of the state machine. And if I see another 0, I should go back to the beginning to start recognizing this state again. And if I see another one, again, this is not part of the sequence that should be recognized. So I should also go to the beginning state again, right? So that was the state machine, right? That was the state machine, right? So so what happened here is that you will see there are states that all outputs goes to the same state, right? So meaning that you can actually merge these 2 states together like this, right? So that's why we got this, right? Oops, I think my animation again made it wrong. So we draw a state machine like this, and then we know there are 2 states, they are essentially the same, right? So we merge them like this. So that's how we get the final answer, right? But another way to think about this is that we can write a state transition table. So the state transition table tells you that, well, let's say the current state S0 is actually meaning that we have something, we are at something else, and S0 means that S1 actually means that you are aggregating 1 0. S2 means that you are aggregating 2 zeros, and S3 are actually 0 0 1. So if you write a state table, you will also find there is a state that goes to the same state, and that should be merged. Okay, so that's the methodology. So right now, what if I change a sequence? And let's say we want to recognize 101. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. The most popular answer right now is C. So can I, well, and actually 70% of you think it's C. Can I have someone explaining why you chose this one? I want a more systematic approach, as I told you. Okay, Xiangying, you are the hero today. What do you think?
Shows yeah, see, because yeah, ideally we want to have 3 transitions, so we need 3 states. So like the first is second state.
Well, first of all, right, for this, what I told you, how many transitions do we need? If
3.
we are not merging any states, how many states do we need? You need 3 transitions, right? So how many states you need by default?
3.
You need 3 transitions, but how many states you need by default?
3 states.
Do you remember this question? How many states?
Oh, we're not merging it. 4.
All right, so how many states do we need for now?
Without merging, then it's 4. Yeah, but I'll just go like not return to the first state then.
Okay, so let's draw it, right? So, well, we now have S0, S1, S2, S3, right? So S0 means that we are starting from somewhere else, right? So if you get a 0, are you staying at S0 or are you go to somewhere else?
Get it? Wait, what's the input?
Well, if input is 0, are you staying here?
Yeah, you're just staying there.
Okay, so I am staying here, right? How about 1?
You can move to S1.
Okay. Okay, how about S1? Right now we are at S1. If you receive a 0, what are you going to do?
Move to S2.
Okay, how about you receive a 1?
At S2, right? Or at S1?
Well, if you are right now at S1,
yeah,
are you going to S2?
No, you're going back to S0. You get a 1.
Are you going back to S0?
Yeah.
Are you sure?
Or you can stay at still stay at S1.
Right, you can
think
stay
it-
at S1, right?
Yeah, it's
Right.
it's
How
either way.
about right now we are at S2?
You need to get a 1 to move to S3.
You get a 1 to move to S3, right? So if you are getting if you get a 0, what happened?
Stay at S2.
No, if you are
Oh,
right
my
now
bad.
at S2.
Oh, you need to if you get a 0, then go back to S0.
Right. And if you get a 1, right, you go to S3, right?
Yeah.
And for S3, right, if you have 0, where are you going? You are going to S0 again, right? And if you have 1, where can you go? If you have another 1,
1 S0 too.
you can go to S1, right? Because it means that you have another 1 now, right? So this is actually
okay.
the state transitions you will see, right? So through this, can we merge anything?
Probably, yes.
Okay,
Professor?
so who are they?
Well, I think we probably can just
Okay, Nicholas.
actually we can't really because
Right.
yeah. No, actually we can't because
Right.
that will cause
Because
a confusion.
Right.
at,
So
S1.
everything has its own meaning, right? So it has 4, right? So right now, you know we need 4. Can you guys pick the ones that would work out? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let me see. So this kind is interesting. So B is the most popular answer with 36%. C is the second most popular, and E also has about a quarter of you. So can I have someone tell us what do you think? Okay, I have Fan Zhong. Okay, what do you think?
I picked C.
You pick C. Okay, so hold on. Xiangying, what do you think?
I pick E.
You pick E. Okay, so it means that you don't believe C would generate the right answer, right?
Yeah.
Okay, so at least can you tell Fang Zhong what's wrong in C?
C. So let's say you put input 1, you go from S0 to S1, but you put 1 again. It goes
Okay, so hold on. My pen cannot pick up you. So you say where are we now?
Let's say we move at S1, you input 1, and go instead of just staying.
Input 1.
Instead of just staying at S1,
then
because it can be the start of another sequence. Because the sequence we're looking for starts with 1, so we don't have to go back to S0.
Right, but is there anything would get wrong here? Right, so if you look at this one, right, what's wrong here is that
actually, yeah, yeah, what? Okay, I say as far starting from S1, you input 1, you go back to S0, then you put in 0 again, just stays in 0, then you put 1 again back to S1, but output 0, so that's wrong.
Right, so the thing is that, right, if you start here 1, 0, 1, right, but this time is outputting 0, right? So this is an exception that in this case, right? So Fang Zhong, do you recognize that there is a potential issue with this state machine?
Yeah, so we can start from any state, right?
Well, you can think about that, right? If you can start from anywhere, but you could start from anywhere. And the other thing is that when you start from, and when you are in anywhere, if there is any incorrect pattern that will be recognized as 1, right? Well, you are at S1 because you already received a 1, right? So if you are right now as S1 and then you get you get another 101, right? 1101. Is that a pattern should output 1? Tell me.
Yes.
Right. But in this case, it will output 0, right?
Oh, okay. Yes, I see.
Right. So that's not what we want, right? Okay. Xiangying, any other thoughts?
No.
Okay, so I have Fang Zhong Li raise your hand again. Okay,
Yeah.
question.
I got confused a little bit. Could you go back to the previous example where you had this kind of question? I just
Which one?
The previous one that looks like this one.
You mean this one?
Oh, yeah. So this one we chose A, right?
We chose A, yes.
Yeah, I just want to wanted to look at it again.
Right. So for this one, even right now we are at S1, right?
Oh,
We got a 0. No matter how many zeros we have, right?
Yeah,
At least finally you get a 1, right? That's the only output.
Yeah, right. Thank you.
Okay. Okay. So other thoughts? Okay, I have Giovanni. Question.
So I was thinking, and I really don't understand what does it mean when you do 0/0 or 1/0 on the finite state machine?
Did you see what I circled?
Sorry, 1 second. No.
On the top left. Did you see my screen?
Okay.
So 1/0 means input 1, and at this we receive input 1, and at this moment we would output 0, right?
Yeah. Okay, thank you.
And that's also consistent with the textbook, I believe.
Professor, sorry, just can you
Yes.
clarify one thing for me? I actually got a little confused.
Mm-hmm.
You said we could start from anywhere, right? Or do we have to start?
Well, you should start with S0, but you could be anywhere, right? Remember, you could be anywhere.
Okay, perfect. Yeah, I just want to be sure. So
So
basic.
no matter, yeah, you could be anywhere because like when you put up your machine, there's no guarantee that you will be somewhere.
So
Right.
the whole point of this is this question is basically asking, is there more than one path that sees 101, and we can start anywhere and make sure that there's no more than one path, and that's basically
There's only one possibility that you will see 101 and output 1.
Okay, perfect. Yeah, I got you. Thank you. That makes a lot of sense.
Well, that's a finite state machine, right? And when you are designing your circuits, you also want to guarantee there is only one possibility you will generate this exact output you want.
Got you. That makes a lot of sense.
Right.
Thank you.
Yeah. So that's what exactly the finite state machine is telling you.
So that's why we can eliminate different answers, because we know it'd be a faulty finite state machine, because if you're giving 101, you might get different outputs, and we want everything to be exactly okay. That makes sense.
Right. So if you see 101, it should always output 1.
Okay. Perfect. Thank you.
All right. So for this question, right? So none of the answer is correct, because there are cases that you see 101, but you don't output 1, right? So there are more practice. You can go back and test, and you can start by like draw the state machine table, and then see like if you can convert a finite state machine from there. And according to the poll that I had, more than 80% of you have learned finite state machine before. So I think before the test, right now, all you need to do is dig out your materials in the past and see how you how did you deal with them in the past. Okay, so we have to move forward, and because that was supposed to just be a recap, not teaching from scratch. So how we can make the finite state machine true, right? So we said, right, this is the theory behind it. So how can we physically implement this finite state machine? So let's go back to the very, very beginning example that we have. Like we want to implement a timer, right? So if I want to have a timer, right, it's a set of logic. We need a set of logic to display the remaining time. And you know how to do this already, right? If you have working on your lab 3, which I believe it should due tonight, right? You should already know how to display the remaining time. If I give you the time, this is what you want to display. And then you need a logic to keep track of what's the current state, because you need that state to for you to know what's the next state, right? So you also need a set of logic, use the current state, and use the new input to transit to a new state and generate the output. And this you also know, right? The only thing we haven't learned so far is a logic to keep track of the current state, right? So that thing is called memory, right? You need a memory to maintain a current state. So let's look at the basic form of the memory. So the basic form of the memory is called SR Latch. So this is the very basic memory, and the SR Latch is something like this. You have a NOR gate, and you have 2 NOR gates, and they are connected like this way, right? So let's not talk about how people discover this kind of a connection, but people always discover things accidentally. Sometimes you ask experts, they don't even know, right? So let's assume that's what a latch like, right? But what happened here is that, okay, so right now, if I raise my S signal to be 1, and in the meantime, if I still keep the reset R signal to be 0. So what turns out is that, right, previously we saw a 0 right here. So it will got propagate to here to do the NOR with 1, right? And when you are doing 1, 0 here, you get a 0 output, and it again becomes the input of here. And when you get 0, 0, you get a 1, right? So in this way, you are setting the current content to be 1, right? And if you notice that for here, the signal I draw here, we have some time difference because there is always some kind of gate delay that you should keep in mind here, right? So right now, what's happening next? If I put this S down to 0 and the reset keep to be 0, right? So what happened here, as you can see, I got a 0 here. So the previous value that's output here is 1, right? So I get 1, 0, and I keep out. I can get the I can in this way get this output to be 0, and it got propagated here. And because this is still 0, so 0, 0 give me a 1 still, right? So what it tells you here is that, okay, right now I raised the signal. First of all, I can do one thing. I raise the set signal to clear, to set the content within this SR latch to be 1. And the next cycle, if I put my signals to be both 0, I can still get a 1. I can still keep the 1 here. Okay. So what else? So right now, if I do the other side, right? If I raise the reset signal, then what would happen here is the reset, well, let's clear the drawing a little bit so that it's easier to see. So right now, if we look at the reset signal, it's right now 1, and the set signal is 0. Right. So, and remember what's previously here, this is 1, right? So this one gets propagated to this gate in the very beginning, and 0, 1 gives us an output 0. And this one gets propagated here, and 0, 1 also get us a 0, right? So it turns out that, okay, right now we are setting the content in SR latch to be 0. And again, there is some time difference here, right? So right now, if I put both signals down to 0, what would happen is that, well, I would be able to receive an output as 0 again, right? So what this tells you is that this kind of circuit, as long as you keep your signal as you well, in a very, as long as you keep one of the signal to be 1, then it will set the content accordingly. If you put both of them to the 0, it will output whatever was previously there. So this is the very, very, very basic form of memory. So if you have the 0, 0 here, it will keep outputting what was previously there. Okay, so right now, what we haven't talked about is the case of 1, 1, right? So, well, but before that, right, let's say, well, right now with SR latch, we have 3 basic functions. We have set function, which would make the store bit to be 1. And reset function would make the store bit to be 0. And a hold function would make both of them 0. Okay, but the case we haven't talked about is what happened when we put a 1, 1. So right now, let's have some more animation out of it. So saying that, okay, right now I have another run of set. So theoretically, I should set my content to be 1 after I put a set and reset, a set to be 1 and reset to be 0, right? That's what we learned. It's essentially the same here, right? However, if both are 1s, what happened is that if you trace or what happened on both signals, you'll figure out, oh boy, the 1 we just set is right now gone, right? So So in this kind of SR latch, the only input that we are not hoping to see is 1, 1, because 1, 1 would actually mess up the content that was currently stored there, right? So how do we solve this issue? How do we solve this issue? So the solution is this. So this part is the original SR latch, right? But if we want to prevent the occurrence of both one, it ends up with that we create another signal called C here. And we change C to 1 only after S and R's are stable, right? Well, if your user behavior is really good, right, you assume they would always put one of them as 0, as 1, or both of them as 0, right? So you can have this kind of inputs, right? However, right, there is a potential that when I am going down from 1 to 0, raising this to from 1 to 0, I would receive a state that both of them are going to be 1. So this is a case we want to avoid. So what happened here is that, okay, so if S and R, they are in transition, we set the C to be 0. And we only set the C to 1 only after both S and R signals are stabilized. So this C we use is essentially the clock that we use in many of the logic. And the reason why we have this clock signal is because we want to make sure that this part of the circuit, they would only function, react to the input of S and R after their signals are stabilized. So this is one design, right? And another thing, well, if you want to further optimize the design of the SR latch, you can actually do this, right? Since you know that your D is, you always want two different inputs to set, right? And turns out that you can also create another type of latch that the input, they are always going to be different, right? So this D, if it's 0, then this part goes to 1 and this part goes to 0. But again, this wire also has its own delay. So you still need a clock to make sure that you only set the signal to 1 whenever whenever the longer signal is arriving at this AND gate, right? So that's the design of D-Latch. And for this D-Latch, if when the clock signal is 0, right, then it turns out that both of the gates will become 0 outputs. So when the clock signal is low, right, no matter what your current input is, it will produce the previous output, right? So that's the rationale behind. I think this should be 1. That's the rationale behind the D-Latch, right? So the basic idea of D-Latch is that, well, we spatially designed, we tweak the design of the input to make sure that at least on the input side, we use only one input, and the input is either 0 or 1, and it would help us to set your content at 0 and 1 or 1 when your clock is on its rising edge. However, if the clock is 0, we just output what's previously in there. So that's the basic idea of D-Latch. So if you look at the design, right, what happened here in D-Latch is that, well, when the clock signal is high, right? It will set the content, change the output. And when the clock signal is low, it would just output what was previously there, right? So for this part, right? For this part, we change the content. We change the content to be 1, right? Because the D is right now as 1, right? So we change the content to be 1. So the output will react immediately. However, when your output when your clock signal is lower, because right now when both clock signals are the clock signals are at 0, you are actually having both of the inputs to be zeros. Then you are going to output what was previously there, right? And right now at this cycle, we didn't change our output input, so we are repeating the same behavior. However, at this at this point, right, the clock signal, because the clock signal is 0, so no matter what you so here, although we change the input of D, but because the clock signal is 0, so effectively your input to the D latch is 0. The RS latch is 0. So it turns out that we still output 0. Right. So this is some kind of this is also means that this kind of circuit, it does work based on the clock signal, and it does prevent the case that if my D signal is changing and it's not stabilized, right? And right now, if right now my D signal is lower, then the output will react immediately. And when the clock signal is low, even though if I have an impulse in a D signal, it's not going to change our output. So that's the basic idea of D-Latch. And however, whenever you are on the high rising edge of the clock, then any change at this point will be captured. So if you try to lower your signal in the middle of the high rising edge, then your output will be changed. So that's an issue of the D-Latch, right? So that's an issue of the D-Latch, right? So the output doesn't hold for the whole cycle, right? So an improved design called D flip-flop, it's actually using 2 D-latches, and one is using a positive edge clock, and the other is acting on a negative edge clock. And the basic idea about this is that whenever the positive edge clock receives the new input, it would propagate to the negative edge clock D-latch as another storage, right? As you can observe from the previous graph, all our latch can only store signal for the half of a clock, right? So if you want to keep the content for the whole clock and only take the input in the very beginning, the solution is that let's just have 2 D-latch, and one of them keep your content on the rising edge, and one of them keep your content on the falling edge. So if you have 2 D-latches chained together, this is the signal looks like. And as you can see, right, with this kind of signal, right, you won't have the situation that if I lower the input signal here, the output is gone. The content won't be gone in this case, right? So that's why right now, based on this, right? Although we have D-latch, but the D-latch is too clock sensitive. So we want to make sure that we have some kind of memory that will be stabilized for the whole clock, and it only take the input at the very beginning of the clock. So that design is called D flip-flop, and that's the only type of flip-flop that I want you guys to remember for this class. D flip-flop. That's the only type of D flip-flop that I want you guys to remember for this class. Its design is actually a combination of 2 D-latches, and the clock signal, one of them is working on the positive edge, the other is working on the negative edge, and one D-Latch would pass its output to another one, so that they can transfer this knowledge to another guy when I am not when my output may be changed. So that's the idea of the flip-flop. All right. So right now, you know there is a D flip-flop can help us to keep the whole content of the circuit, right? What do we need to physically implement a timer, right? The logic to keep track of that, right? And however, we also learned that for the logic to keep track of the current state, you also need a control signal that help us to transit to the right state at the right time. So that's in addition to memory, which we just introduced the flip-flop as the basic form of memory. We also need a clock. So let's talk about the basic concept of a clock. And when we talk about a clock, I encourage you to think about, put things all together. Thinking about this carry look ahead adder. And what is all right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so the most popular answer is C. Can I have some of you tell me what do you guys think? Well, most of you think it's C and you think it makes sense. But let me tell you, C is not the right answer. The right answer is actually A. Well, sorry, it's actually B, right? The right answer is actually B. At the time we take the output, we cannot get the correct result. Why is that? Why is that? The answer is not C. Why is that? This is the right answer. Why is this? Okay, so here's the thing, right? When we try to take output after 4 delays, and for the carry look ahead adder, how many gate delays we need? We need a total of 16 gate delays, right? So think about that, right? Even though I wait for another gate delay, it's not going to give me the right output, first of all, right? And the second thing, right? even I wait for another 12, it's still not going to give you the right delay. Because think about the circuits. Some of the circuits, they would react immediately within 4-gate delays. The 4-gate delays is the critical path of the circuit. However, there are some part of circuit like this A0, B0, A1, B1, A2, B2. They only need 2-gate delays to get changed, right? So when you are taking the output, right? When you are taking the output, you would never get a chance to get the right output if you try to change your input after 4-gate delays. Because your signals are already messed up. Your signals are already messed up. So that's not going to happen. That's not going to happen. So that tells us that it's really important for us to know the gate delays required for the whole thing to finish, to set up your clock signal correctly. So the basic idea of clock signal is a pulsing signal for enabling latches. And so in case, right, I receive an input and if my signal is not set correctly, then all my input content will be gone. And those inputs that supplies my LU, they will also be incorrect, right? So you need a clock signal to be set long enough to keep all your inputs stable for the whole cycle, right? So the basic idea of a clock is the pulsing signal for enabling latches, which we talk about. And in synchronous, it's a sequential. For the clock period is the time between the pulsing of each pulse starts, right? So for example, for this clock signal, right, the whole clock signal is like this. It's 20 nanoseconds, right? And the clock cycle, right, that you see here, we have 1, 2, 3, 4, right? So actually we have 4 clock cycles and a duty cycle, right? What does that mean by duty cycle? Remember, for the D flip-flop that we talk about, it only reacts on the input in the first half of the cycle. So only when the clock age is high, we would react on the input. So your clock cycle, duty cycle means the time your clock is high, right? So for this case, the high cycle is 10 nanoseconds, the low cycle is 10 nanoseconds, and the clock frequency is actually 1 over your cycle time. That's how you get 50 megahertz here, right? Okay, so this is one of the questions, the last question before our midterm, and this question, the clock part is also the clock is also part of our midterm. So make sure that I want to make sure that you guys know what is clock before the midterm. So can you guys show me your understanding about the clock? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like most popular answer is C. But can I have some of you telling me why do you think the answer is C, and what are the two that you recognize? Okay, I have fun zone. What do you think?
I thought there were 3 that were right.
Okay, so what are the 3?
The first one, second one, and the fourth one.
Okay, why the first one is correct?
Frequency is a 1 over clock period.
Right, what's a clock? Where can I find a clock period?
The clock period is from the beginning of a positive edge to the end of a negative edge.
Right, so that's the clock period, right? And it's 4 nanosecond, and 1 over 4 nanosecond is actually 250 megahertz, right? So this one is correct. Duty cycle.
And a duty cycle is when it's how much of a period of time is this clock positive in a period.
So how much is that?
3 nanoseconds in 4 nanosecond period.
Right, so that's 75%, right? Okay, what's the other one you recognize? So if 1 is correct, 3 is definitely not correct, right?
Yeah, right. So I think 4 is also correct.
Right, because we have 1, 2 complete clock cycles, and we have 1 incomplete clock cycles, right? So the answer is going to be 3. Okay, so from the quiz today, I am sure there are a lot of stuff we have to figure out, we have to study before you guys take the midterm. So and it's really important because midterm is one of the midterm and the final. They are actually one of the most. They are the 2 most expensive items. So some of you keep asking about, like, if I miss an assignment, if I miss a lab, or well, if I miss a quiz, can I make up? The answer is definitely no, because I mean they are only very, very minor to regrets. But for midterm and the final, it's not the case, right? It's 20%, 25%, this big, right? So so there are a few things that I want you to know. First of all, for the lab 3 due to 9, I know you guys spend a lot of time working on the lab, and I know you spend a lot of time working on other midterms, but don't forget we also have midterm next Thursday, and I will have a midterm review next Tuesday. But it would be better an idea that you spend some time working on the slides and those reading quizzes we have, and especially, this time we are going to do an online test, and the easiest form to make your question online is multiple choices. So we are going to have tons of multiple choices questions, like what we had in the class, what you have ever taken in reading quiz, and like what you did in Zybooks. Right, so these are all the things that I want you to be aware before you attend the midterm review next Tuesday. And in the next midterm review next Tuesday, I will try to re-emphasize on the important high-level bits, and also try to clear up those frequently made mistakes. Other than that, I would talk to you in office hour tomorrow, or maybe